Section 1 Introduction. We're going to discuss a new approach to improving the performance of transformers, a type of machine learning model, without significantly increasing computational costs. Recent research suggests that to make the most of a given computational budget, we need to scale up both the size of the model and the amount of training data. One promising solution is to use a technique called sparse mixtures of experts, MOEs. In recent times, several successful methods have been proposed that activate only certain paths in the network for each token, a unit of data, in language, vision, and multimodal models. This is the essence of sparse MOE transformers. The challenge lies in deciding which modules, often referred to as experts and typically multi-layer perceptrons, MLPs, should be applied to each input token. Various techniques have been developed to find the best match between tokens and experts. These include linear programs, reinforcement learning, deterministic fixed rules, optimal transport, and greedy algorithms that select the top K experts per token or the top K tokens per expert. Often, heuristic auxiliary losses are needed to ensure that all experts are used evenly and that no tokens are left unassigned. These challenges can become even more difficult when dealing with out-of-distribution scenarios, such as small inference batch sizes, new inputs, or transfer learning. We're introducing a new approach, called soft MOE, that addresses many of these challenges. Instead of using a sparse and discrete router to assign tokens to experts, soft MOEs perform a soft assignment by mixing tokens. Specifically, we calculate several weighted averages of all tokens, with the weights depending on both the tokens and the experts. Each weighted average is then processed by its corresponding expert. Soft MOE models avoid many of the challenges associated with the discrete procedure at the heart of sparse MOEs. Traditional sparse MOE algorithms learn some router parameters, and the source of gradients usually comes from two places: the multiplication of expert outputs with the selected routing scores, and auxiliary losses that enforce some desired behavior and also depend on the routing scores. It's been noted that these mechanisms often perform no better than random fixed routing. Soft MOE avoids this problem by updating every routing, or mixing, parameter based on every single input token. Soft routing can provide stability while training a router. It's been observed that during training, large portions of input tokens can simultaneously change discrete routes through the network, leading to training challenges. Furthermore, hard routing can be difficult with many experts, with most works training with just a few dozen. We demonstrate that soft MOE can scale to thousands of experts and is balanced by design. Finally, there are no batch effects at inference, where one input can affect routing, due to limited expert capacity, and hence prediction, for other inputs. Soft MOE L16 outperforms VIT-H14 on upstream, few shot, and fine-tuning tasks while requiring almost half the training time and being twice as fast at inference. Moreover, soft MOE B16 matches VIT-H14 on few shot and fine-tuning tasks and outperforms it on upstream metrics after a comparable amount of training. Notably, soft MOE B16 is 5.7 times faster at inference despite having 5.5 times the number of parameters of VIT-H14. We also demonstrate soft MOE's potential to extend to other tasks. We train a contrastive model text tower against the frozen vision tower, showing that representations learned via soft routing maintain their benefits for image-text alignment. Section Summary. Sparse mixtures of experts, MOEs, have been proposed as a way to scale models without incurring the full computational cost. However, the discrete optimization problem of assigning modules to input tokens in sparse MOE transformers can be challenging. To overcome this, soft MOE models perform a soft assignment by mixing tokens, avoiding the challenges associated with the discrete procedure. Soft MOE outperforms other methods, such as VIT, in terms of performance and training time, and it can scale to thousands of experts while maintaining balance. Additionally, soft MOE shows potential for tasks like image-text alignment. Section 2 Soft Mixture of Experts. We're going to discuss the soft mixture of experts, soft MOE, routing algorithm. This algorithm is visualized in a figure in the paper. Let's start with the basics. We have a sequence of input tokens, represented as X. This sequence is in a space of dimensions m by d, where m is the number of tokens and d is the dimension of each token. In the soft MOE layer, we use a set of n expert functions. These functions are applied to each individual token. In practice, all experts use the same function but with different parameters, typically a multi-layer perceptron, MLP. Each expert processes p slots, and each slot has a corresponding d-dimensional vector of parameters. We represent these parameters as phi. The input slots, represented as tilde x, are the result of combining all the m input tokens, x, in a specific way. This is done by applying a softmax function over the columns of x, phi, which we call the dispatch weights, D. After that, we apply the corresponding expert function to each slot, i.e., on rows of $x, to get the output slots, represented as $y. Finally, we compute the output tokens, y, as a combination of all output slots, y. The weights for this combination are computed in a similar way as before, by applying a softmax function over the rows of x, phi. We call these the combine weights, C. In the design of sparse MOs, we replace some of the transformer's MLP blocks with soft MO blocks. Typically, we replace the second half of MLP blocks. The total number of slots is a crucial parameter of soft MO layers. This is because the time complexity depends on the number of slots, not the number of experts. For instance, we can set the number of slots equal to the input sequence length to match the computational complexity of the equivalent dense transformer. Section summary. The soft mixture of experts, MO, algorithm uses a set of expert functions applied to individual tokens in a sequence. The algorithm computes dispatch weights, D, by applying a softmax over the columns of the input tokens multiplied by the expert parameters. The output tokens are obtained by applying the expert functions on the input slots, and the combine weights, C, are computed similarly. Soft MO blocks can replace a subset of MLP blocks in the transformer model, and the number of slots is an important hyperparameter. Section. Fully differentiable. At the heart of all sparse mixture of experts, MO, algorithms, there's a task of matching tokens and experts. This task is typically subject to certain capacity and balance limitations. Different algorithms tackle this task in various ways. For example, the token choice router selects the top-ranked experts for each token, as long as there's room in that expert, meaning the expert hasn't reached its capacity. The expert choice router, on the other hand, picks the tokens with the highest capacity scores for each expert. There are also more complex, and often more expensive, methods for calculating these assignments, such as those based on linear programming algorithms, optimal transport, or reinforcement learning. However, almost all of these methods are discrete, meaning they're not differentiable. In contrast, all operations in soft MO layers are continuous and fully differentiable. We can think of the weighted averages with softmax scores as soft assignments, which is what inspired the name of our algorithm, rather than the hard assignments typically used by sparse MO methods. Traditional routing mechanisms often encounter problems like token dropping, where some tokens aren't assigned to any expert, or expert unbalance, where some experts receive far more tokens than others. These issues can significantly affect performance. For example, the popular token choice router suffers from both issues, while the expert choice router only suffers from token dropping. Soft MOs, however, are essentially immune to token dropping and expert unbalance. This is because every slot is filled with a weighted average of all tokens, and all weights are theoretically strictly positive thanks to the softmax. This ensures a more balanced distribution of tokens among experts. Section summary. Sparse MO algorithms involve an assignment problem between tokens and experts, with different algorithms relaxing or approximating the solution in various ways. Soft MO layers, on the other hand, offer continuous and fully differentiable operations, using weighted averages. With softmax scores as soft assignments instead of hard assignments. Soft MOs also address issues like token dropping and expert unbalance, which can significantly impact performance in classical routing mechanisms. Section. Fast. We'll now discuss the speed of the soft mixture of experts, MO, layer, its features, and its deterministic nature. The speed of the soft MO layer is primarily determined by the total number of slots, which is its main hyperparameter. Each input applies a certain number of multilayer perceptrons, MLPs, and the total number of experts doesn't affect this calculation. Whether we have a few experts with many slots each, or many experts with a few slots each, the cost will be the same if the total number of slots is the same. However, we need to ensure that the number of slots is at least equal to the number of experts, as each expert must process at least one slot. The soft MO layer has the advantage of completely avoiding slow sort or top K operations, which are typically not well suited for hardware accelerators. As a result, the soft MO layer is significantly faster than most sparse MO layers. The soft MO layer also has features of both sparse and dense MO layers. The sparsity in sparse MOs comes from the fact that expert parameters are only applied to a subset of the input tokens. However, soft MOs are not technically sparse, as every slot is a weighted average of all the input tokens. Every input token fractionally activates all the model parameters, and all output tokens are fractionally dependent on all slots and experts. However, soft MOs are not dense MOs either, where every expert processes all input tokens, as each expert only processes a subset of the slots. Under capacity constraints, all sparse MO approaches root tokens in groups of a fixed size and enforce balance within the group. When groups contain tokens from different sequences or inputs, these tokens often compete against each other for available spots in expert buffers. As a result, the model is no longer deterministic at the sequence level, but only at the batch level, as some input sequences may affect the final prediction for other inputs. Models using larger groups tend to perform better and have higher computational costs. However, when groups contain tokens from a single sequence, the model is forced to use every expert on every input sequence, which may lead to more generalist experts. Changing the group size between training and inference can also be problematic due to potential shifts in token to expert assignments. The soft MO layer elegantly avoids these challenges. Since it combines all tokens in each input sequence, we simply set the group size to be a single sequence. Every expert handles tokens from every input, which may somewhat limit the amount of high-level specialization. However, this also means that it is deterministic and fast on a per-example basis, unlike typical instances of sparse MOs. Section Summary. Soft MO is a faster alternative to sparse MOs because it avoids slow sort or top K operations. While sparse MOs only apply expert parameters to a subset of input tokens, soft MOs fractionally activate all model parameters for every slot, making it not technically sparse. Soft MOs also provide per-sequence determinism by combining all tokens in each input sequence, making it faster and, for example, deterministic compared to sparse MOs. Section. Time complexity. Let's discuss the time complexity of our model. We'll start by assuming that the cost of a single expert function is proportional to a constant, k. The time complexity of a soft MO layer is then proportional to the product of the number of tokens, the number of experts, the number of slots per expert, and the model dimension, plus the product of the number of tokens, the number of slots per expert, and the constant k. If we choose the number of slots per expert to be proportional to the ratio of the number of tokens to the number of experts, the cost reduces to a value proportional to the square of the number of tokens times the model dimension, plus the product of the number of tokens and the constant k. The beauty of this is that each expert function has its own set of parameters. So, by increasing the number of experts and adjusting the number of slots per expert accordingly, we can increase the total number of parameters without affecting the time complexity. Furthermore, when the cost of applying an expert is high, the term proportional to the product of the number of tokens and the constant k becomes the dominant factor. This makes the overall cost of a soft MO layer similar to that of applying a single expert to all the input tokens. Even when the term proportional to the square of the number of tokens times the model dimension is not the dominant factor, it's equivalent to the cost of self-attention in transformer models, so it doesn't become a bottleneck. Now, let's talk about normalization. In transformers, MO layers often replace the feed-forward layer in each encoder block. When we use pre-normalization, as is common in modern transformer architectures, the inputs to the MO layer are normalized. This can cause stability issues when we increase the model dimension, as the softmax function tends to produce a one-hot vector as the model dimension approaches infinity. To address this, we replace the input and the expert function with their L2 normalized versions, and multiply the normalized expert function by a trainable scalar. This normalization doesn't significantly affect the model's quality for relatively small model dimensions. However, with this normalization in the soft MO layer, we can increase the model dimension and/or the learning rate. We use this approach in all our experiments. Finally, let's discuss model distribution. When the number of experts becomes very large, it's not feasible to fit the entire model in the memory of a single device, especially during training or when using MOs with large model backbones. In these situations, we use standard techniques to distribute the model across multiple devices. Distributing the model does add some overhead to the model's cost, which isn't captured by the time complexity analysis based on flops that we discussed earlier. To account for this, in all our experiments, we measure not only the flops, but also the actual time taken in TPU v3 chip hours. Section Summary. The time complexity of a soft MO layer is determined by the per-token cost of a single expert function, which is O, K, and the number of slots per expert, page. By increasing the number of experts, N, and scaling P accordingly, we can increase the total number of parameters without impacting the time complexity. Additionally, the normalization technique used in MO layers can cause stability issues when scaling the model dimension, but the proposed normalization in the soft MO layer allows for larger model dimensions and increased learning rates. When the number of experts is large, distributing the model across multiple devices adds an overhead cost that is not captured by the time complexity analysis based on flops. Section 2.4 Connections with other methods. 2.4 Comparisons with other techniques. There are numerous existing methods that combine or blend input tokens to decrease the length of the input sequence. They typically use attention like weighted averages with fixed keys to mitigate the high computational cost of self-attention that increases quadratically with the length of the sequence. While our method of calculating dispatch and combine weights is similar to these techniques, our objective is not necessarily to shorten the sequence length. In fact, we restore the original sequence length after applying the combine weights to the outputs of the experts at the end of each soft-mo layer. Our approach also shares some similarities with multi-headed attention, beyond the use of softmax in weighted averages. The H different heads in multi-headed attention can be seen as different, linear, experts. However, there is a key difference. If M is the length of the sequence and each input token has a dimensionality of D, each of the H heads processes M vectors of size D divided by H. The resulting M vectors are then combined using different weights for each of the M' output tokens, i.e., the attention weights, on each head independently. The resulting vectors, each of dimension D divided by H, from each head are then joined together to form a vector of dimension D. In contrast, our experts are nonlinear and combine vectors of size D, both at the input and output stages. Our method also has some similarities with other Mo techniques that use a weighted combination of the expert's parameters, instead of routing the examples in a sparse manner. These methods are also fully differentiable, but they can be more computationally expensive because 1. They need to average the parameters of the experts, which can become a time and/or memory bottleneck when experts with many parameters are used, and 2. They cannot leverage vectorized operations as extensively as soft and sparse Mo's, since every input uses a different weighted combination of the parameters. We suggest referring to the computational cost discussion that addresses these issues. Auto-regressive decoding. One of the key features of soft-mo is its intelligent merging of all tokens in the input. This makes the application of soft-mos in auto-regressive decoders challenging, as the causal relationship between past and future tokens must be maintained during training. Although causal masks used in attention layers could be used, care must be taken to avoid introducing any correlation between token and slot indices, as this could bias which token indices each expert is trained on. The use of soft-mo in auto-regressive decoders is a promising area of research that we plan to explore in future works. Section summary. Existing methods often merge or fuse input tokens to reduce sequence length, but our soft-mo approach aims to maintain the original sequence length while weighting the outputs of experts. Multi-headed attention is similar to soft-mo in terms of weighted averages, but our experts are nonlinear and combine vectors of size D. While there are connections with other Mo works that use a weighted combination of expert parameters, they can be more computationally expensive and less efficient in utilizing vectorized operations compared to soft-mos. The use of soft-mo in auto-regressive decoders is a promising area for future research, but caution must be taken to preserve causality and avoid introducing correlations between token and slot indices. Section. Lazy experts and memory consumption. We've conducted extensive research and found that it's generally best to allocate one slot per expert. This means that instead of giving one expert 2 slots, or a mix of tokens, it's more efficient to have 2 experts, each with 1 slot. We believe this is because slots from the same expert tend to align and provide minimal additional information. Also, a single expert might not be flexible enough to handle very different slot projections. We've detailed this in the appendix. As a result, our soft-mo model tends to use a large number of experts. While the cost is comparable to the dense backbone, the memory requirements can be quite high. We've conducted 3 types of image classification experiments. 1. Training Pareto frontiers. We've compared dense VIT models of various sizes, small, base, large, and huge, with their sparse counterparts. We used the most common routing techniques, tokens choice, experts choice, and soft-mo routing. We studied the relationship between training flops and performance, and training time and performance. We found that soft-mo outperforms all other methods. 2. Inference time optimized models. We've conducted longer training runs, which we refer to as overtraining. Compared to VIT, soft-mo significantly improves inference speed for small models, S, B, and overall performance for large models, L, H. 3. Model ablations. We've examined some key aspects of soft-mo routing, like the number of experts, slots per expert, etc., and compared them with other routing algorithms. We've identified the optimal configurations for soft-mo and the sources of its performance improvements. We've pre-trained our models on JFT4B, a proprietary dataset with over 4 billion images covering more than 29,000 classes. During pre-training, we typically evaluate the models on 2 metrics: upstream validation precision at 1 on JFT4B, and ImageNet 10-shot accuracy. The latter is calculated by freezing the model weights and replacing the head with a new one that is only trained on a dataset containing 10 images per class from ImageNet -1K. Finally, we provide the accuracy on the validation set of ImageNet-1K after fine-tuning on the training set of ImageNet-1K, 1.3 million images. Section Summary. In this section, the authors discuss the use of lazy experts in the context of memory consumption. They find that using one slot per expert is more optimal than feeding one expert with two slots. They also show that soft MO tends to require a large number of experts, leading to increased memory requirements. The authors then present three types of experiments on image classification, comparing dense ViT models with their sparse counterparts and concluding that soft MO outperforms other approaches. They also provide details about the training and evaluation data used in their experiments. Section 3.2 Sparse Routing Algorithms. In this section, we'll be discussing sparse routing algorithms and how they compare to popular mixtures of experts, MO, routing algorithms. We'll also talk about how we trained Pareto optimal models. Let's start with the routing algorithms. One method is the tokens choice, where each token selects the top K experts based on their routing score. As we increase K, we generally see better performance, but this comes with a higher computational cost. We've found that using batch priority routing, BPR, can greatly enhance the model's performance, especially when K equals 1. We use top K routing with BPR and K values of 1 and 2. We also fine-tune the number of experts. Another method is the expert's choice, where the experts select the top C tokens based on their routing scores. Here, C represents the buffer size. We usually set the product of the number of experts, E, and C equal to the product of a capacity multiplier, C, and the total number of tokens in the group, T. When C equals 1, all tokens can be served by the combined efforts of the experts. However, it's common in this type of routing for some tokens to be chosen by multiple experts while others aren't chosen at all. We experimented with C values of 0.5, 1, and 2. Next, let's talk about training Pareto optimal models. We trained various models, including VITS-8, VITS-16, VITS-32, VITB-16, VITB-32, VITL-16, VITL-32, and VIT-H-14, along with their sparse counterparts. For the sparse models, we considered three routing algorithms: token choice, expert choice, and soft MO. We trained several variants of each model, adjusting K, C, and the number of experts as needed. In total, we trained 106 models. All models were trained for 300,000 steps with a batch size of 4,096, using inverse square root learning rate decay. Our results showed that, on both training cost and performance metrics, soft MO significantly outperformed both dense and other sparse approaches for any given computational or time budget. We've listed all the models, along with their parameters, performance, and costs. We've also compared soft MO individually to dense, token choice, and expert choice models. Section Summary. In this section, the authors compare different routing algorithms for sparse models in the context of mixture of experts, MO. They evaluate two types of routing algorithms: tokens choice, where tokens select the top K experts, and experts choice, where experts select the top C tokens. They experiment with different values of K and C and train a total of 106 models. The results show that soft MO outperforms dense and other sparse approaches in terms of performance and cost for any given flops or time budget. Section 3.4 Long Training Runs. We've conducted extensive training runs to evaluate the performance of the soft mixture of experts, soft MO, model at larger computational scales. We've carried out two main experiments. In the first experiment, we trained Vision Transformer, ViT, and soft MO models of varying sizes, from small to huge, for 4 million steps. The results showed that the soft MO models performed exceptionally well. In the second experiment, we continued training some of the soft MO models beyond the optimal point suggested by standard dense scaling laws. This allowed the sparse models to utilize the extra capacity to steadily improve their performance. The result was highly efficient soft MO models that were notably cost-effective during inference. We also compared the performance of soft MO models with large-scale vision transformers. We trained several soft MO models on the JFT dataset, using a similar setting to that used by vision transformers. We replaced the last half of the blocks in various ViT models with soft MO layers, each with 128 experts and one slot per expert. We trained models with parameters ranging from 1 billion to 54 billion. Despite the slightly longer wall clock time required by large soft MO models due to the extra data transfers needed for model parallelism, the soft MO models outperformed the vision transformer models within the same compute budget. For example, the SoftMo S16 model performed better than the VIT B16 model on the JFT and 10-shot ImageNet datasets, and also improved fine-tuning scores on the full ImageNet dataset, even though its training and inference cost was significantly lower. Similarly, the SoftMo B16 model outperformed the VIT L16 model upstream, and was only half a point behind after fine-tuning, while being 3 times faster and requiring almost 4 times fewer floating point operations per second, flops. Lastly, the SoftMo L16 model outperformed the dense H14 model while being around 3 times faster to train and serve at inference. Section Summary. In this section, the authors conducted long training runs to test the capabilities of SoftMo models at larger computational scales. They trained VIT and SoftMo models of different sizes for millions of steps and found that SoftMo models outperformed vision transformer models for a given compute budget, even though they were faster and required fewer flops. This demonstrates the effectiveness and efficiency of SoftMo models in comparison to traditional dense models. Section 3.4.2 SoftMos optimized for inference. We're excited by the fact that soft mixtures of experts, SoftMos, with smaller backbones can match the quality of larger vision transformers, VITs. So, we decided to further train these smaller backbones to create high-quality models that require very little computational power for inference. Even with this extra training, the total training time is similar to that of larger VIT models. For these extended training periods, we found that longer cooldowns, where the learning rate is gradually reduced to 0, work well for SoftMo. As a result, we increased the cooldown from 50,000 steps, which we used elsewhere, to up to 500,000 steps. Our main findings are as follows. A SoftMo B16 model, trained for 1000 TPUV 3 days, outperforms a VIT H14 model trained for a similar amount of time. Moreover, it's 10 times cheaper in terms of floating point operations per second, flops, and 5.7 times faster in real time. It even almost matches the performance of the VIT H14 model if we double the training budget of the VIT H14. The SoftMo L16 model outperforms all other models significantly, while being almost twice as fast at inference as the VIT H14. Next, we wanted to find the best configurations for SoftMo models. We looked at the following factors. 1. Optimal number of slots per expert. We found that 1 or 2 slots per expert work best. We proved this by keeping the total number of slots, which determines the computational cost of the model, constant, and changing the number of experts, i.e., the slots per expert. 2. Optimal number of experts. Roughly the same number of experts as input tokens work best when using 1 slot per expert. The model then has a similar computational cost in terms of flops as its dense equivalent. We demonstrated this by increasing the number of experts in training models for the same amount of time, and then identifying the best performing model. 3. Architectural algorithmic ablations. To understand the source of the benefits, we compared SoftMo to several ablated versions. These included routing token I deterministically to expert I, fixed uniform dispatch, combine weights, and others. 4. Mo layers placement. We also conducted an additional ablation regarding where to place Mo layers. These are our findings, and we believe they provide valuable insights into the optimization of SoftMo models. Section Summary. SoftMos with smaller backbones can achieve the same quality as larger vision transformers, leading to higher quality models at a lower inference cost. Longer cooldowns during training are found to be effective for SoftMos, resulting in models that outperform VIT models while being significantly cheaper and faster at inference. Optimal configurations for SoftMo models include 1 or 2 slots per expert and roughly the same number of experts as input tokens. Comparisons with ablated versions and different placements of Mo layers are also explored. Section 3.5.1 Number of experts and slots per expert. When we use the soft mixture of experts, Mo, method in a specific architecture with a certain input sequence length, we need to decide on the number of experts and the number of slots for each expert. The total number of slots determines the workload applied in the Mo layer, excluding the minor routing cost. If the total slots exceed the number of input tokens, the model will need more floating point operations per second, flops, than dense transformers, as more tokens will be processed in the Mo layer. On the other hand, if the slots are fewer than the original tokens, SoftMo will save some computational power compared to dense transformers. In our experiments, we used a Vision Transformer S16 backbone, trained for 300,000 steps with a batch size of 4096. The Mos have expert layers in their last 6 of 12 blocks. We kept the total compute constant and compared different configurations. We set the total number of slots to 4096 and trained models with varying numbers of experts. Mo algorithms often struggle to scale well with a large number of experts, over 100. The model sizes ranged from 38 million, with 2 experts, to 9.7 billion parameters, when using 4,096 experts. Our results showed that soft Mo scales well with an increased number of experts. The best configurations were 2048 and 4,096 experts, with 1 or 2 slots per expert, respectively. In contrast, Experts Choice and Tokens Choice did not scale well with the number of experts, and performance declined after 512 experts. Due to sorting leading to increased computational overhead, the Sparse Mo step time increases substantially with more experts, which is not the case for soft Mo. From our analysis, we set the number of slots per expert to 1 and then determined how many experts to use. More experts will increase the cost through more slots. Both for soft Mo and Experts Choice, more experts performed better, up to 1024. After matching the total training time for each model by adjusting the number of training steps, we found that the optimal number of experts for a given training budget is around 128 or 256 experts. The number of input tokens is 196, which corresponds to the minimum number of experts that does not lead to a strong token bottleneck, many fewer than 196 slots, in the Mo layer. For any number of experts, soft Mo outperforms Experts Choice. Both models have the same capacity, but Experts Choice is significantly more expensive, especially with a large group size. We also explored how soft Mo behaves when increasing the number of slots per expert and looked at the strong correlation between the learned slot parameters in this case. Section Summary. When using soft Mo, the number of experts and slots per expert must be determined. The total number of slots affects the computational workload in the Mo layer, with more slots requiring more flops. Soft Mo performs well with increased experts, while Experts Choice and Tokens Choice do not scale well and experience degraded performance after a certain number of experts. Additionally, soft Mo outperforms Experts Choice in terms of cost and capacity. Section 3.5.2 Algorithmic Ablations, Identity and Uniform Routing. We've been exploring how soft Mo, our model, learns to blend different pieces of information, or tokens, for each expert. We've done this by testing 2 different methods: identity routing and uniform mixing. In identity routing, each token is assigned to a specific expert without any mixing. For example, the first token goes to the first expert, the second token to the second expert, and so on. In uniform mixing, all tokens are combined in the same way, by averaging them uniformly. This is done both when assigning tokens to experts and when combining the outputs from the experts. However, in this case, we need to make sure that each expert is initialized randomly and independently. If we don't do this, the extra capacity provided by different experts won't be used, and we'll just end up with duplicates. We also tested 2 hybrid methods: soft, uniform, and uniform, soft. In soft, uniform, we learn to mix tokens when assigning them to experts, but we average all expert outputs uniformly. This means that every input token is updated in the same way before the residual connection. In uniform, soft, we fill all slots with the uniform average of the input tokens, but we learn to mix the expert output tokens based on the input tokens. Our results show that learning to mix tokens both when assigning them to experts and when combining the expert outputs is crucial for good performance. We also found that mixing tokens when assigning them to experts is slightly more important than when combining the expert outputs. Dense, another method we tested, performed worse than all the other methods. Next, we wanted to see if the representations our model learned could also be used effectively for other tasks. We decided to test this using a popular method called image-language contrastive learning. We followed an approach where the image tower is first trained on an image classification task, and then frozen while the text encoder is trained on a dataset of image-text pairs. We used the models we had trained on JFT in the previous section and compared their performance on several downstream applications. For contrastive learning, we trained on WebLI, a proprietary dataset consisting of 10 billion images and their alt texts collected from the internet. The image encoder was frozen, while the text encoder was trained from scratch. Our results showed that the gaps we observed in image classification were also present in this setting. For example, Soft Mo L16 performed better than VIT L16 by more than 1% and 2% on ImageNet and CIFAR 100 shot, respectively. However, the retrieval numbers were generally modest. Section Summary. In this section, the authors explore different ablations of the Soft Mo algorithm, testing the impact of different routing and mixing strategies for input tokens. They find that learning to mix tokens for dispatching and combining is crucial for good performance, with dispatch mixing being slightly more important. Additionally, the authors conduct contrastive learning experiments using image-language pairs and find that the performance gaps observed in image classification tasks are preserved in this setting, with SoftMo outperforming ViT on ImageNet and CIFAR 100 zero-shot tasks. Section 5 Model Inspection. In this section, we'll delve into the various aspects of the model's routing process. We're particularly interested in how different tokens contribute to slots. Even though there's no dropping in SoftMo, it's still possible for some tokens to contribute minimally to all slots if their logits are significantly lower than those of other tokens. We're curious to see if some tokens disproportionately contribute to slots. We examine the distribution of the total weight each token provides to slots, which is the sum of the weights across all slots. This was calculated using a batch of 256 images, each with 196 tokens, on a SoftMo S16 fine-tuned on ImageNet. We found that there's a significant number of tokens that contribute more to slots, and this pattern is somewhat consistent across layers. Roughly 2 to 5% of the tokens provide a total weight above 2, while between 15% and 20% of the tokens contribute up to 0.25 in total weight. The last layer is slightly different, with a softer tail of token contribution. We also wanted to understand how different slots contribute to the output tokens. We focused on the scenario where there's one slot per expert. We estimated the total contribution of each expert, or slot, by averaging their corresponding coefficients in the linear combinations for all output tokens in a batch. Depending on the layer, some experts can impact output tokens between 3 and 14 times more than others. We also looked at how many input tokens are needed for each slot to achieve a certain cumulative weight in its linear combination. The distribution varies significantly across slots. For some slots, the top 20 to 25 tokens account for 90% of the slot weight, while for others the distribution is more uniform and many tokens contribute to fill in the slot. Generally, slots tend to mix a large number of tokens, unlike in standard sparse MOs. To give you a better understanding of how slots average input tokens, we visually represented the linear combinations for 8 different slots for a given image. We shaded patches inversely proportionally to their weight in the slots. Note that all token representations are eventually combined into a single one before being passed to the expert. These plots correspond to a SoftMo S16 with 128 experts and 1 slot per expert, and we selected 8 out of the 128 slots to illustrate how different slots tend to focus on different elements of the image. Section Summary. In this section, the authors analyze the routing process of the model by examining token contributions to slots, expert contributions to outputs, and the number of input tokens per slot. They find that there is a heavy tail of tokens that provide a stronger total contribution to slots, with around 2 to 5% of tokens having a summed weight above 2. Additionally, they observe that some experts can impact output tokens between 3x and 14x more than others. The distribution of input tokens required to achieve a certain cumulative weight in a slot's linear combination varies significantly across slots. Finally, they provide visual representations of how different slots focus on different elements of an image. Section 6 Discussion. In our discussion, we've noted that sparse models can sometimes encounter infrastructure-related issues, which might have hindered their widespread use. These models were initially designed to handle extremely large model sizes, which often necessitates their distribution across multiple devices. This distribution process can increase communication costs, as it requires the transfer of additional activations, gradients, or expert parameters between devices. This is also the case with SoftMos, where the experts might be distributed as well. However, with the advent of modern dense models that are also distributed due to their large size, this difference is becoming less significant. Moreover, the advantages of sparsity become more apparent with smaller model scales. This is true both in previous studies and with our SoftMo, aligning with the industry's current demand for quicker inference. We introduced SoftMo, a novel sparse transformer architecture that sidesteps the issue of assigning tokens to experts discretely, a common problem in sparse mixture of experts models. By combining input tokens into linear combinations before sending them to experts, we can train a model that is both quick and fully differentiable. We conducted a series of image classification and image language contrastive learning experiments to compare the performance of dense models with several sparse methods, including tokens choice, experts choice, and SoftMo. The results suggest that SoftMo is remarkably effective, often outperforming other methods while also being more computationally efficient. Looking ahead, figuring out how to handle causal masking for language decoders presents an exciting and potentially impactful avenue for future research. Section Summary. Sparse models, including SoftMo, have faced challenges in terms of infrastructure and communication costs due to their distributed nature. However, as modern dense models have also become distributed, the gap between sparse and dense models in this aspect has closed. The benefits of sparsity are particularly evident in smaller model scales, making SoftMo a fast and fully differentiable model that outperforms other sparse methods while being computationally cheaper. Future research should focus on addressing causal masking for language decoders.